Imagine Earth, not as we know it today, but as it existed 780,000 years ago, a time long before recorded history, before the rise of civilizations, and before the invention of even the simplest tools we take for granted. Picture vast, untouched plains stretching as far as the eye can see, a landscape dominated by raw, untamed nature. Inhabit these plains with strange beasts, megafauna unlike anything we see roaming the Earth today. Creatures adapted to a world vastly different from our own. A world with no cities or calendars, no roads or written languages, a pristine wilderness untouched by the hand of modern civilization. A world operating on a completely different timescale. Now imagine that on one ordinary day in this extraordinary world, the planet's magnetic field began to act strangely. An invisible force, vital to life as we know it, started to behave in an unpredictable manner. If our ancestors, the early humans of that era, had possessed a lodestone, a naturally magnetic rock, it would have spun wildly, erratically, offering no reliable direction. Its pull weakening and shifting, the magnetic force that usually aligns it with the north would have become faint and unreliable. The very essence of direction would have been lost. This was no mere glitch, no temporary anomaly. It was the start of a global event, a planet-wide transformation that would unfold over centuries. This event is known to us today as the Matuyama-Brunès reversal, a period etched in geological history. It was a time when Earth's magnetic poles flipped, a phenomenon that turned the world's magnetic orientation on its head. Over thousands of years, the magnetic field weakened dramatically and grew increasingly chaotic, its familiar structure dissolving into disarray. Imagine a world where multiple magnetic poles appeared and vanished, creating a confusing and unpredictable magnetic landscape. Creatures that relied on the magnetic field for navigation, such as migrating birds and sea turtles, would have been utterly lost, disoriented in a silent, invisible storm of magnetic confusion. Their internal compasses spinning uselessly. The field's strength dropped to a fraction of its normal intensity, leaving the planet vulnerable. This weakening left Earth exposed to a barrage of cosmic and solar radiation, normally deflected by the strong magnetic field. The atmosphere would have borne the brunt of this assault. Auroras, the shimmering displays of light usually confined to the polar regions, may have danced far from the poles. These spectacular light shows would have painted the skies in unexpected places, gracing tropical skies with ethereal glows. Eventually, after millennia of turmoil, the chaos subsided. The molten iron deep within Earth's core, the source of the magnetic field, settled into a new configuration, and the magnetic field stabilized once more, but this time it was reversed, its polarity flipped. North became south, and south became north, a complete inversion of the planet's magnetic orientation. A compass, if one existed, would now point to Antarctica instead of the Arctic, a clear indication of the profound change that had occurred. The world's magnetic orientation had flipped, a fundamental shift in the planet's very nature. This dramatic change is written into the very rocks beneath our feet, a permanent record of a planet in flux. This isn't science fiction, a fantastical tale of a distant world. It's a real chapter in Earth's history, a documented event that shaped our planet. The story of the last great flip, the Matuyama-Brunès reversal, serves as a powerful reminder of our planet's dynamic and ever-changing nature, and the immense forces that shape our world over vast stretches of time. Earth isn't just a rock. It's alive with a churning, molten core of iron and nickel. This swirling metal acts like a giant dynamo, generating a powerful magnetic field. The field forms the magnetosphere, a protective bubble that shields us from the sun's deadly solar wind. Without it, our atmosphere would be stripped away, as happened to Mars. The magnetosphere channels solar particles to the poles, creating the auroras, nature's light show and proof of our shield at work. For centuries, humans have used the magnetic field for navigation, and countless animals rely on it to migrate. Even today, our technology and many species depend on this invisible force. It's a silent guardian, shaping life and technology on Earth. The magnetic field is essential for our survival. A magnetic pole reversal is a fascinating phenomenon where Earth's magnetic north and south poles essentially swap places. It's a dramatic shift in the planet's magnetic field, a bit like a cosmic dance of the poles. This reversal doesn't involve the physical planet turning upside down, of course. Instead, it's the invisible magnetic field that surrounds Earth that undergoes this change. This field, also known as the geomagnetic field, acts as a protective shield. The process begins with the magnetic field destabilizing. It doesn't happen overnight, it's a gradual weakening and disruption of the established order. As the field weakens, it becomes more complex and chaotic, breaking into multiple, weaker poles scattered across the globe. It's a period of magnetic confusion before the field eventually settles into a reversed state, with north becoming south and vice versa. What's truly remarkable is that this isn't a rare or unusual event. Magnetic pole reversals are a normal and recurring part of Earth's long and dynamic history. The evidence of these past reversals is meticulously recorded in ancient rocks, providing scientists with a valuable timeline of Earth's magnetic behavior. When lava cools and solidifies, magnetic minerals within the rock align themselves with the prevailing magnetic field, effectively locking in the field's direction at that moment in time. By studying these magnetic signatures in rocks of different ages, scientists can piece together a detailed timeline of past magnetic flips, revealing the frequency and patterns of these events. However, despite our understanding of the process, reversals remain unpredictable in their timing. In the past, they've occurred relatively frequently, sometimes happening every 200,000 years or so. But then, there have been extended periods where tens of millions of years pass without a single reversal. The driving force behind these reversals is the turbulent and complex motion of liquid iron deep within Earth's core. This molten iron acts like a giant dynamo, generating the magnetic field. The chaotic nature of this process makes it virtually impossible to predict with any precision exactly when the next magnetic flip will occur. It's a bit like trying to predict the exact moment a storm will break. It's important to remember that a reversal is not an instantaneous event. It's a slow and gradual process that unfolds over thousands of years, not moments. During the long transition period, the magnetic field weakens significantly, leaving the planet more vulnerable. In some cases, the field strength can drop to as little as 10% of its normal intensity, substantially reducing its protective capabilities. This weakening means that more solar radiation, in the form of charged particles from the sun, can penetrate the atmosphere. Additionally, the Earth is exposed to higher levels of cosmic radiation, which consists of high-energy particles from beyond our solar system. This increased radiation has the potential to impact both life and technology, potentially disrupting electronic equipment, satellite operations, and even power grids. However, it's crucial to emphasize that the main consequence of a magnetic reversal is a weaker shield, not an instant catastrophe that wipes out life on Earth. The scientific evidence overwhelmingly supports this conclusion. Magnetic pole reversals are slow, chaotic, and an intrinsic part of our planet's natural and ongoing geological cycle. The last full magnetic reversal occurred approximately 780,000 years ago, a long time in human terms, but a blink of an eye in geological time. Over its long history, Earth has experienced countless magnetic flips, and each time, the planet has weathered the storm and life has continued to thrive. The Earth's magnetic field, an invisible shield protecting us from cosmic radiation, is in constant flux. It's a dynamic force, generated by the swirling molten iron deep within our planet's core. But what if we could hear this invisible force? What would a magnetic reversal sound like? The field itself is silent, a phenomenon we typically perceive through instruments and data. But scientists, driven by curiosity and a desire to make the invisible visible, have ingeniously turned its data into sound. They've embarked on a journey to sonify the Earth's magnetic field. Using precise satellite measurements, capturing the subtle shifts and undulations of the magnetic field, researchers have meticulously crafted an eerie soundscape, a sonic representation of a magnetic reversal in action. This is not just data, it's an experience. It starts as a steady hum, a low, constant drone that represents the magnetic field in its relatively stable state. This is the baseline, the foundation upon which the sonic drama will unfold. Then, as the simulated reversal begins, the steady hum breaks into a series of crackles and metallic clangs. These sharp, jarring sounds represent the increasing instability of the field, the turbulent forces at play deep within the Earth's core. The chaos in the sound mirrors the chaos in the core, the roiling, churning molten iron that generates the magnetic field. It's a direct auditory representation of the complex geophysical processes happening far beneath our feet. The sound reflects the emergence of multiple poles, the magnetic field becoming increasingly complex and unpredictable, with compass needles spinning wildly as they struggle to find a stable direction. As the flip progresses, the initial steady hum gradually fades, losing its dominance as the reversal intensifies. The familiar stability is giving way to something new and uncertain. The fading hum is replaced by a cacophony of unstable noises, a jarring and unsettling mix of crackles, pops, and groans that paint a vivid picture of a planet undergoing a profound transformation. This artistic project, born from scientific data, allows us to feel the drama of a magnetic reversal in a way that raw numbers and graphs simply cannot convey. It's an emotional connection to a scientific phenomenon. We're able to experience the reversal viscerally, not just read about it in a textbook or scientific paper. The sound bypasses the intellect and speaks directly to our senses. It's a powerful tool, not only for public outreach, making complex science accessible and engaging, but also for gaining new scientific insight by exploring the data in a completely different way. Listening to the field's music, its sonic representation, reveals subtle patterns and hidden rhythms that might otherwise be missed when analyzing numerical data alone. This project demonstrates how creativity can bridge the gap between science and emotion, fostering a deeper understanding and appreciation of the natural world. It helps us grasp the immense scale and power of Earth's inner forces, the geological processes that shape our planet and influence our lives in profound ways. The sound of a magnetic reversal is undeniably unsettling, a stark reminder of the dynamic and sometimes unpredictable nature of our planet. It serves as a powerful reminder of the planet's restless heart, the molten core that drives the magnetic field and sustains life on Earth. Through sound, we gain a new perspective, experiencing the invisible drama unfolding beneath our feet, the hidden processes that shape our world. If a pole reversal began today, the first signs would be technological, not geological. Satellites would suffer more malfunctions as the weakened field lets in more solar particles. Navigation systems relying on magnetic compasses would become unreliable, forcing us to depend solely on GPS and other methods. Power grids would be at greater risk from solar storms, increasing the chance of blackouts. Auroras would appear far from the poles, lighting up skies in unexpected places. The world would witness beautiful, unsettling reminders of a planet in flux. Our infrastructure would need major upgrades to cope with these changes. The process would unfold over centuries, not overnight. A reversal would challenge our technology but not end civilization. For animals, a magnetic reversal would be a crisis of navigation. Birds, sea turtles, salmon, and even insects rely on the magnetic field to migrate and find their way. During a flip, their internal compasses would fail, leading to confusion and lost migrations. Populations could decline as animals struggle to adapt. Yet life is resilient. Species have survived many reversals before. Animals use other cues like the sun, stars, and smell, and evolution favors those who adapt. The transition would be tough, but not an extinction event. Nature finds a way, even when the map changes. Despite dramatic headlines, magnetic reversals aren't linked to mass extinctions. Fossil records show no correlation between flips and die-offs. Our ancestors lived through the last reversal without catastrophe. Even at 10% strength, the atmosphere still shields us from most harmful radiation. Radiation levels might rise slightly, but not to deadly levels. The ozone layer remains intact, so UV protection continues. Reversals are slow, natural processes, not signs of doom. The real challenges are technological and navigational, not existential. Life adapts. Earth has flipped many times and life has always endured. The planet's history proves resilience is the rule. A reversal is a challenge, not an apocalypse. Today, scientists watch the South Atlantic anomaly, a region where the magnetic field is unusually weak. Satellites passing through this area face more radiation, risking malfunctions. Astronauts even see flashes of light as cosmic rays hit their eyes. The anomaly is growing and drifting, possibly hinting at deeper changes in Earth's core. It could be a precursor to a reversal, or just a temporary fluctuation. Studying the anomaly helps us prepare for future changes in the magnetic field. Should we worry? The field is weakening, but reversals take thousands of years. The real risks are to our technology, not to life itself. Scientists monitor the field with satellites and observatories, giving us time to prepare. The challenge is engineering, protecting satellites, power grids, and navigation systems. With vigilance and innovation, we can adapt. The magnetic field story is one of change, not catastrophe.